Hi, this is Mark from HowrTech. In this video, I'd like to discuss the exponential aspect of virus propagation. I will also present a very simple simulation that I developed using LabVIEW. When I discuss with people, and when I hear a politician on TV, I realize that there are two concepts about the propagation of a virus within a population that sometimes they don't understand. Incubation period and exponential progression. Here I want to discuss exponential progression. As humans, we tend to assume that things are linear. However, the propagation of a virus is exponential. I think it's worth here to spend some time to express it mathematically. Let's assume that the number of persons infected by a virus at a given time t is n index t. This number of infected persons is a function of the number of infected persons at the previous time t minus 1. This function is simply the number of persons previously infected multiplied by coefficient for different factors. The first coefficient t is for transmission, and this coefficient is typically a characteristic of the virus itself. It indicates how easily the virus transmits from one person to another. The second factor is e for exposure, and this is the coefficient that's going to take into account the number of persons that an infected person is exposed to. This is the coefficient that would be affected by measures put in place by authorities to slow down the spread of a virus. A third coefficient is d for detection. This coefficient takes into account the probability that an infection would be detected. This coefficient does not affect the actual number of infection. However, it affects the number that can be actually measured. I'm going to neglect this coefficient. Let's combine the coefficient e and t into a single coefficient r that we're going to call rate. If the rate r is larger than 1, it means that between time t minus 1 and t, the number of infected persons increases. If we assume that the rate is constant, we can use the number of infections at t minus 2 to calculate the number of infections at t minus 1, which means that the equation can take this form. So we can repeat this transformation d times, and if d is the number of days and n index 0 is the number of cases on d0, the equation takes this form. If we apply logarithms to both sides of the equation and after logarithm manipulations, we can see that if we plot the logarithm of the number of cases as a function of days in a log linear plot, the slope of that curve would be equal to the logarithm of the rate of increase of cases. So this is exactly what I have done in an Excel spreadsheet for a few countries for the Covid-19 pandemics using the following references. Using the log s function within Excel, I use the last 10 points of each curve to estimate the rate of increase of each of those curves. Those rates are indicated here. We can see that as of March 26th, the rate of increase varies between 1.11 and 1.46. That means that, for example, for the US, with a rate of 1.33, the number of cases increases by 33% every day, whereas for Italy, it increases only by 11%. We can see from the shape of the curve of cases in Italy that the measures taken by the authorities in Italy seems to decrease the rate as a function of time. Whereas in the US, the rate has been constant for the past 25 days.
And that's the problem with exponential growth. You should use early detection as soon as you suspect that there might be a virus and containment methods. But as soon as you detect that exponential growth, you should start using severe mitigation methods. Things are made worse by the incubation period, which I do not address here. I have illustrated exponential progression by creating a VI that simulates the growth of algae in a pond. The VI consists in two loops, a main loop and an algae growth loop. The algae is drawn as an ellipse by the main loop. The size of the ellipse is proportional to the amount of algae. The algae is grown at a rate of 30% per day, and the level of algae is plotted in a waveform chart that is in a log linear scale. The code of this VI can be accessed using the link in the description of this video. Let's run this VI. We can see that the algae grows in the waveform chart, even though we don't see any visible algae in the pond. It's not until day 40 that the algae is visibly apparent, and by then the pond is overtaken within a few days. I hope you enjoyed this video. If you have any question or comment, do not hesitate to put them in the comment section of this video, or you can contact me directly. Bye.